Now I would like to talk about most common properties about matrices and their inequalities within the context of control systems, the mostly common ones. All right, so let's start with M. And M, basically P and N dimension, we say it is a mapping from Rn to Rp. For example, let's take a vector x in Rn, then y equals to m multiplied by x. We can represent this as m1 transpose all the way up to mp transpose multiplied by this vector x. In other words, we can write it as the inner product, or m1 transpose x, all the way up to mp transpose x. So resulting y is in Rp. So basically this matrix, or this mapping, and this linear mapping is called a matrix because, and it is called as a P by N matrix because it takes an n-dimensional vector. When it is multiplied by P, it converts it a P-dimensional vector. So it converts X and Rn dimension to Rp dimension. All right, so this is, we're gonna call it matrix, which is a linear map. We can do some simple example. For example, let's say M is 1, 2, 3, 4, 5, 6. Let's say X is 0, 1, 2. Y, basically their multiplication, 1, 2, 3, 4, 5, 6, multiplied by 0, 1, 2. Basically, when you multiply this together, 1 multiplied by 0, 2 multiplied by 1, 3 multiplied by 2. So 1 multiplied by 0 plus 2, 1, 3, 2. Likewise for the second row, 4, 0 plus 5, 1 plus 6, 2. You are going to get 8 and 17. Again, this was three-dimensional. It converted to a two-dimensional vector. So this is 2 by 3 matrix. All right, for a special case when M is square, M square means it is n by n. We say that this matrix, square matrix M, is invertible, or M inverse invertible, or M inverse exists if and only if basically determinant M is not equal to 0. I would like to talk momentarily about the determinant, but if M is invertible, we can write M inverse M equals to M inverse, which is the identity matrix, a spatial matrix that looks like 1, 1, 1, 1 on the diagonals, and everywhere else is 0. All right, so before I define the determinant, I would like to make one note. So please don't write M over N when you deal with matrices, because it is not clear if it refers to N inverse M or M N inverse. So, and to convince yourselves, basically get two matrices with compatible dimension, multiply them with each other, you are going to see immediately that they don't equal to each other. All right, now I would like to talk about the determinant. So for this, let's say M is an n by n matrix. determinant of M is nothing but the eigenvalues of this matrix M, x1 multiplied by, lambda 1 multiplied by lambda 2 multiplied by all the way lambda n. So this is an n by n matrix. It is going to have n eigenvalues. You can write this fancier if you like using the product notation, I equals to 1 to n lambda I, where lambda I belongs to the spectrum of M. Spectrum of M is a special notation that is used to denote the eigenvalues of the matrix M. Now, remember, M inverse exists, or M is invertible, when determinant of M is non-zero. Now, looking at the definition of the determinant, if matrix M has all non-zero negative or positive eigenvalues, so once you make this multiplication, you are going to have non-zero determinant of M. So we say that equivalent way to say M inverse exists or M invertible is to say that if M doesn't have a zero eigenvalue, then it is invertible. Now, I will also define eigenvalues momentarily, but I would like to write two interesting properties about the determinant. Let's say you have two matrices A and B of compatible dimension. Determinant of AB is nothing but determinant of A multiplied by determinant of B. Now, you can also write determinant of A inverse as 1 over determinant of A. So some neat properties about the determinant that one should know who is working on control systems. About eigenvalues briefly. Basically, eigenvalues of a square matrix, say A, basically are nothing but the roots of determinant lambda I minus A equals to 0. If you take this determinant of lambda I minus A, set it to 0 and solve for the lambdas, you are going to find the eigenvalues of matrix A. For example, let's say A is 1 minus 1 minus 1, 1. It is basically lambda I minus A becomes lambda minus 1, 1, 1, lambda minus 1. Taking the determinant of this matrix, we are going to have lambda 1, 1, 1, lambda minus 1, which is, this is not the absolute value, another notation to denote determinant, at least for 2 by 2 matrices. Lambda minus 1 to the power of 2 minus 1, this product minus this product. We have lambda to the power of 2 minus 2 lambda plus 1 minus 1. We have lambda square minus 2 lambda, or we have lambda minus 2. We are going to set it to 0. So this matrix A given here, its eigenvalues are lambda 1 equals to 0, lambda 2 equals to 2. Is it invertible? No, because it has a 0 eigenvalue. If these lambda 1 and lambda 2 eigenvalues are non-zero, then we would conclude that matrix A is invertible. All right, so like the determinant or eigenvalues, trace of a matrix is also common. So let's talk about trace. Again, the main purpose of this video, if you learned this stuff before, is to refresh your mind or simply overview some of the stuff that we use in control systems papers. So let's consider a n by n matrix. Definition of a trace is nothing but summation of I equals to 1 to n, I. What does it mean? For example, let's say 1, 2, 3, 4, this matrix A, its trace, basically you are summing its diagonal elements, 1 plus 4, it is 5 basically in this case, applying the definition. Now, some properties about trace. Trace of A equals to trace of A transpose. Take its transpose. A transpose is what? You take these, write it like this. Trace of A transpose, 1 plus 4, again 5. So trace of A transpose. You can also verify this within the context of an example. Now, interestingly, trace of A equals to summation of I equals to 1 to n eigenvalues of matrix A. And here, lambda I belongs to the spectrum of A. If you remember, right, for this matrix A, 1 minus 1 minus 1, 1, its eigenvalues were 0 and 2. Now, if you sum them up, you are going to get 2 here. Or if you apply this traditional notation, the trace of A is 1 and 1, it is 2. Within the context of an example, you can immediately see that trace of I is summation of the eigenvalues of matrix A. Two important properties about trace that we see from time to time. Trace of AB equals to trace of BA. A and B are some matrices of compatible dimension. Equals to trace of A transpose B transpose equals to trace of B transpose A transpose. This part actually coming from here. Basically, let's take this trace of AB must equal to trace of AB transpose. And remember, AB transpose is nothing but B transpose A transpose. This comes first, then this comes second. So we have trace of B transpose A transpose. Likewise, if we apply this to here, you are going to get this part of the story. So this is basically an important property to know. You can generalize it to several matrices of compatible dimension. Trace of ABC equals to trace of BCA equals to trace of CAB. Basically, this is in a particular order, A, B, and C. So BC stays here, A comes here, AB stays here, C comes here. This order must be maintained for this property. For example, it doesn't equal to some arbitrary order, right? So this is wrong. That part is the correct part. When we deal with matrices, we also talk commonly non-negative definiteness and positive definiteness. And I would like to give a clear definition about these because from time to time I see some mistakes even in some technical papers. First of all, non-negative definiteness. Let's start with that. Matrix A, n by n, is non-negative definite. If A equals to A transpose, it must be symmetric. And all eigenvalues of A basically greater or equal to 0. If this is the case, we show A as A in R plus, including the origin, it can include 0, n by n, and of course some authors also show like this. I found this a little more precise. No, so one thing to remember here, for a given square matrix, it is all eigenvalues can be equal or greater than 0. But to say non-negative definite, A needs to be symmetric. And I will give you an example immediately after these definitions. An equivalent definition of non-negative definiteness is this: for a given arbitrary vector x, x transpose ax is equals to or greater than 0, we say that A is non-negative definite if it is symmetric. So this is something to check, equivalent notation. Now, and of course this is for all x in Rn. Now, about positive definiteness, again a square matrix n by n, we say it is positive definite if A equals to A transpose, it must be symmetric, and all eigenvalues of A are greater than 0 strictly. In this case, we show A in R plus or some others. Simply do this. Again, the key property here is this. All right, an equivalent notation is for a given arbitrary vector x, if for any x this holds for all x including Rn, of course excluding x equals to 0 vector, then we say A is positive definite. So now let's do two examples. In the first example, A is 1 minus 1 minus 1 1. It is symmetric. A will equal to A transpose. Actually, since it is symmetric, we found the eigenvalues of this matrix 0 and 2. One of them is 0, but other one is 2. So we can say it is non-negative definite since some eigenvalues are 0, some eigenvalues are positive. We can also apply the equivalent notation. Let's consider some arbitrary vector x1, x2. X transpose ax, if we multiply with each other, it has x1 minus x2 to the power of 2. We cannot say this is strictly positive. It is less than, it is basically, it can be 0. So, right, when x1 equals to x2, it can be 0. The best we can say is that it is non-negative definite, applying the equivalent notation. Now, about non-negative definiteness, I would like to mention an interesting fact before moving to the second example. Something to know. Let's say A is some arbitrary n by m matrix. If you find A transpose, it will be non-negative matrix as well, m by n in this case. Or if you write A transpose A, in this case it will be m by m non-negative matrix. It will be symmetric. So these are two, you can obtain non-negative definite matrices by multiplying them from left or right by their transpose. All right, so now the second example will be on why we care about A equals to A transpose in the definitions of non-negative definiteness and positive definiteness. For example, A is 1, 0, 10, 2. It is certainly not symmetric. A doesn't equal to A transpose. If you find its eigenvalues by applying the definition, it will be lambda 1 will be 1, lambda 2 will be 2. So these videos will be full of information, and if a matrix has this upper triangular structure, its eigenvalues are located on its diagonal as well. So something good to know. Anyway, turning our attention back, we have a matrix, its eigenvalues are positive. So why do we need symmetry? Why do we need A transpose A? A equals to A transpose. Right? All right. let's apply the equivalent notation. X transpose AX for some x1, x2. If you do this multiplication, you are going to get x1 to the power of 2, 10 x1, x2, and 2 x2 to the power of 2. Now, let's start giving some examples. Let's say x1 is 1, x2 is minus 1, and here x is x1, x2. I am just taking some specific numbers. In this case, this will be 1 to the power of 2. This will be 2 multiplied by minus 1 to the power of 2. But this will be minus 10. So there exist some values of x1 and x2 such that x transpose AX is less than 0. But our eigenvalues were positive. That's why we care about positive definiteness, to claim again. Very important, to claim matrix, a square matrix A, non-negative definite or positive definite. First, you need to ensure A equals to A transpose. Otherwise, we cannot talk about non-negative definiteness or positive definiteness, period. All right, interesting stuff to know. Now I am jumping to matrix norms. Right, vectors have norms, so matrices also have norms. All right, so here I will start with the definition. P norm defined as the supremum x not equal to 0, ax p divided by p. There are also different norms. I will just refer to in this video the norm induced by vector p norm. All right, so now to define matrix norms, we have some interesting definition, but in practice, how we compute these norms. Let's say A is in n by m. One norm is basically max I, j, n, I equals 1 to m, a, I, j. All right, let's do an example to understand. Let's say 1, minus 1, 1, minus 2, 2, minus 2, 3, minus 3, 3. A1, applying this definition here, max of 1 plus minus 2 plus 3, basically doing this, comma, I don't have space, so I will write here. I am continuing with this one, minus 1 plus 2 plus absolute value of minus 3. Absolute value is coming from here. And the third one is 1 plus minus 2 plus 3. So looking all these numbers, they all equal to maximum 6, 6, 6. So the answer is 6. So they are all the same, so I just pick one of them. I would not directly jump to 2 norm. I would like to talk about the infinity norm because it kind of have a different but is slightly similar notation to the 1 norm. A infinity is defined now max I, 1, I, m. We were using n here, now using m here. Instead of m, now we are going to use n. I equals to 1, absolute value of I, aj. So now consider the same example and find A infinity here. Instead of looking at like this, we are going to look at these. In other words, we are going to look at maximum of 1 plus minus 1 plus 1, comma, minus 2 plus 2 plus minus 2, comma, 3 plus minus 3 plus 3. So we have maximum of 3, 6, and 9. In this case, going with the largest 9. Right? So it was 6 for one norm of A, and infinity norm of matrix A is 9. So this is how you compute one and infinity norms of a matrix. The definition of the two norm is more straightforward. Basically, A2 is the maximum eigenvalue of A transpose A. And you need to take the square root. And this is also called, I use this to make some definitions, sigma of max of A. Basically, this is nothing but the largest singular value of matrix A. Something good to know, I just wanted to mention. Now I will continue with the norms. We also have Frobenius norm, a Frobenius norm, F stands for Frobenius, is basically I equals 1 to m, j equals 1 to n, aij to the power of 2, 1 over 2 or square root. This is called the Frobenius norm. So comparing two norm with the Frobenius norm, we can say A2 is less than or equal to A Frobenius. You can just illustrate this within the context of an example. Now, I would like to also write triangle inequality. Basically, A plus B, this holds for any matrix norm. So I will write with star A star plus B star, something very useful to know. And so now how you use these norms, and like for example, if you have an energy or Lyapunov function, you are trying to find an upper bound, or if you have simple upper or lower bound computations, you use these norms. Let me give you one example. Let's say you have a sign indefinite term plus or minus x transpose A y. Let's say we would like to upper bound this. First of all, this is upper bounded by, like this is first of all acknowledge this is scalar. If you take its absolute value, you are going to have basically x transpose AY. We are writing the same thing. Now it is upper bound can be found as you can start with x transpose A to y2. Basically, I apply Cauchy-Schwarz inequality, right? This is a vector, this is a vector. You can also write this as, if you wish, A transpose A to more precisely apply Cauchy-Schwarz, x transpose y, remember, x2, y2. I just wanted to convert this. This is our new x transpose. So I wanted to write it like this. All right, now we can apply in a similar fashion. This is upper bounded by A or A transpose to x2, y2. This is how you upper bound things. This is the least conservative way to upper bound things, and you can also use Frobenius norm, which is completely unnecessary in this case. F x2 y2, since a2 is greater af. You can do this. This is for sign indefinite. When you have sign indefinite terms, we usually upper bound these like that. Now, When you have sign definite terms, sign definite means you know if it is positive definite or negative definite or non-negative definite. So for example, let's say you have a positive definite matrix A in R plus m by n, then you know x transpose AX is positive definite by definition. So it is less than or equal to minimum eigenvalue of A, x to the power of 2, and upper bounded by maximum eigenvalue of A multiplied by x to 2. So basically, this is by definition, this side is equals to 2 norm x2 to the power of 2. You can also upper bound this as a Frobenius x to the power of 2 for sign definite stuff. And when you have sign indefinite, just don't use eigenvalues. And basically this holds for sign definite stuff. Don't use eigenvalues, just upper bound things like this when you have sign indefinite terms. All right, so now how we compare matrix norms with each other in this final portion of the video. A2 greater than A Frobenius that you know now, R A2. Now A is an n by n matrix or m by n. R here refers to the rank of A m by n. I will define rank in a second. Bear with me for now. Let me write the other two stuff. 1 over square root of n A infinity is less than or equal to A2 m A infinity, and 1 over square root of m A1 A2 less than or equal to square root of n A1. Now, so these are how these norms compare with each other. Here, rank is the maximum number of linearly independent columns or rows of A. For example, let's consider this A1 minus 1 minus 1. Looking at the columns, right? So you can take this column, multiply by minus 1, and you produce the exact this column. So in this case, these two columns depending on each other, so its rank is 1. Or if you have a matrix like this, 1, 1, 0, 2, so can we take one column and produce another one? Not really in this case. And in this case, basically, this is its rank of this matrix 2, whereas this red matrix's rank was 1. All right, so I would like to also mention maybe about the null space and range space of matrices and conclude this video. Let's let V be an n by n matrix. Null space basically of this matrix is shown as NV, which satisfies for x in Rn 0 equals to Vx. So vectors x when multiplied by V, if they produce 0 output, then these vectors belong to the null space or kernel. Let's also write this. We use also kernel since matrix is a linear map, so null space is a kernel of a linear map. Now the range space shown as R v, definition-wise, x in Rn, when you multiply v by x, it produces something. So this is called the null space. And interesting property, dimension of the null space of v plus the dimension of the range space of v equals to n. The dimension n by n matrix is n. All right, let's do an example. Let's consider the same example that we used in multiple places. Let's find the null space first. Applying the definition, 0 equals to Vx, or equivalently, 0 equals to 1 minus 1 minus 1 multiplied by x1, x2. We are going to have x1 minus x2, x2 minus x1. So as you see, to get 0, x1 must be equal to x2. In this case, we say null space of V can be any vector. It can be 1, 1, 2, 2, 3, 3, 4, 4, minus 5, minus 5. In order not to complicate things, we use a neater way. We rate span. Any vector that spans 1, 1, meaning that take this multiplied by some scalar, it can be 5, 5, 10, 10. So this span notation denotes vectors of 1, 1, 2, 2, minus 2, minus 2 structure. If you multiply this matrix V by vectors like this, you will get 0 output. Now let's find the range space, applying to y equals to Vx. Here, basically y1, y2 equals to the same thing, right? Vx. So we have x1 minus x2, x2 minus x1. We are going to see y1 equals to minus y2. In this case, range space of V span vectors of 1 minus 1 structure. It can be 2 minus 2, 5 minus 5, or minus 2, 2. So all belongs to this span. So null space of V contains one vector, so dimension is 1. Range space of V contains one vector, it is dimension of 1. This is 2 by 2, so n is 2. So this also holds. Okay, I hope you will find this video helpful, and I can maybe mention one more thing before I forget. I am preparing these videos by looking at my notes. I also wanted to share 2 norm of A is less than A1, A infinity, let's write square root. This is a spatial case of Hölder's inequality. Let's also keep it in your notes, so something good to know. And with this, I can conclude the video.